This is the cover of Optical Signal Processing, published in 1992 by Anthony Vanderlugt. I never met Vanderlugt, but I know Baha Saleh, who was the editor of this series, well, and has been a leader in our field for many years. Vanderlugt trained with Leith and with H.H. Hopkins in Britain, and then he joined NC State. Actually, my advisor, Dimitri Soltis, interviewed with NC State prior to joining Caltech, where he presumably discussed optical signal processing with Vanderlugt. And then, of course, Professor Soltis worked on very similar kinds of optical processing throughout the 1980s. So what we see here is a couple of illustrations from Vanderlugt's textbook. The upper illustration of a laser and transforms is a very nice illustration to be happy to have in my book, but the lower one is kind of a low contrast image published in this book from 30 years ago. So what the upper one shows is you collimate a laser, you put a signal field on the input plane, and then a lens takes the Fourier transform, and so you could do a Fourier transform processing with optics as opposed to doing it digitally. And what we see at the lower curve is Fourier transforms of different components. So streets are periodic, and they produce a kind of periodic Fourier transform pattern. Trees in the ocean, presumably waves on the ocean, are creating a kind of diffraction pattern that is recognizable that an optical processor could detect. Now, in computational imaging, we do a variety of physical processing with lenses, usually to condition the field for measurement, but it's a very important part of the overall computational process. And then we couple that with digital imaging. What Vanderlugt did here with analog Fourier transforms has largely been supplanted by digital Fourier transform methods. But throughout computational imaging, we see that the physics of processing and the processing in digital systems are highly interconnected. When we say interconnected in optics, this is the kind of thing we mean, that we have optical interconnections, in this case for constructing a deep neural network. Professor Soltis went from optical signal processing to development of optical neural networks in the 1980s, which I was honored to work with him on, and today we see this work has been revived in this deep diffractive network from Oskan's group at the University of California, Los Angeles, and we see this parallel between electronic interconnections or neural interconnections and interconnections in optical systems. Like Vanderlugt's work, this optical processing hasn't really taken off as a competitor for electronic imaging, but optics and processing in systems, and especially how we process systems at the or how we process fields at the interface of imaging systems, remains a core topic. So today we begin our discussion of how lenses process the field. Computational imaging. Episode 36, the coherent impulse response. Episode 35 discussed the transmittance function of lenses. And we showed that a lens is described by a transmittance function which is quadratic in the transverse coordinates with a parameter f corresponding to the focal length. So a point source here at the front focal plane is collimated into a plane wave after encountering the lens. Today, we want to talk about lens transformations. So the transformation between an input plane in the xy plane, where we have a distribution f of xy, to a distribution g of x double prime, y double prime in the output plane. And we'll have a distance z1 between the input plane and the lens, and a distance z2 between the lens and the output plane. And we wish to calculate the field as it propagates from the input plane to the lens and to the output plane. This is a linear system. What that means is that if we had a superposition of two different fields, f of x, y, with the measurement at the output plane would be the linear superposition of those fields. In this kind of linear system, we can calibrate, or we can calculate the response of the system using the impulse response. So we look for single inputs in the input plane, find what the output is for that impulse, and then we can integrate with the impulse response over the input plane to have a general mapping between any input distribution and the corresponding output distribution. To calculate the impulse response, we can look at what happens to an impulse propagating through the system. So the initial field, the impulse at position x naught, y naught, we will assume produces this Fresnel wavelet propagating toward the lens. And then when this Fresnel field hits the lens, we modulate by the transmittance function of the lens as shown here. And then we're going to propagate from the lens to the output plane, which involves convolution with the Fresnel kernel between those planes. So we take the field that we have due to the input shown here, multiplied by the transmittance function of the lens. We've added here the pupil function of the lens to limit the support over which the lens operates on the field. And now we're convolving this field on the surface of the lens with the propagator, the Fresnel kernel, from the lens to the output plane. So this is it. This is our impulse response between the input points x naught, y naught, and the output points x double prime, y double prime. A little bit complicated. Let's see if we can simplify it. So here's this distribution again between the input points x naught, y naught, and the output points x double prime, y double prime. We can expand the quadratic terms in these exponentials and see if we can simplify this a little bit. And if we do that, we get this form, that the quadratic terms over x double prime and x naught, y naught, we can remove from the integral since we're integrating just over x prime and y prime. And then we have these terms inside of the integral, and we have this phase delay lambda over, or z1 plus z2 over lambda would be the phase delay between the two planes. Okay, so that's our simplified version of the impulse response, still quite a bit complicated. One thing that we can do now is choose specific values of z1 and z2, particular conjugate planes in the system, and see if we can't simplify this a bit further. One interesting choice is to choose z1 equals z2 equal f. So this is the relationship between the field at the front focal plane of the lens and the field at the back focal plane of the lens. Each of these distances is f. Now we know kind of what this should look like, because if we had an impulse here at the front focal plane, we'd expect a plane wave at the output focal plane, which means we're turning a impulse at the front focal plane into a harmonic value, plane wave propagating in a certain direction at the output plane. Conversely, if we had a plane wave here, so we have a wave that would be described as e to the I 2 pi ux, that would turn into an impulse at some point proportional to u in the output plane. And so a constant or a harmonic value in the input plane turns into an impulse at the output plane. An impulse at the input plane turns into a harmonic value at the output plane. That's a relationship that's a Fourier relationship. So let's see if we can't derive that from our equations. Now, if we choose f1 equal, or z1 equals z2 equals 1 over f, then this term is going to just turn into 1 over f. And then here we're going to have z1 and z2 equal to f. We could extract out, and this would turn into x prime, x naught plus x double prime. And then here we'd have a lambda over f. So this is a term linear in x prime and y prime in its exponents. That's a Fourier transform kernel with the frequency here would be x naught plus y x double prime over lambda f. This is a Fresnel kernel. So we have a term in x prime squared and x and y prime squared times some constant, but the proportionality to the quadratic form is a Fresnel kernel. So if we ignore this pupil function, this is a Fourier transform of the Fresnel kernel. Now, the Fresnel kernel is going to be oscillating at a very high frequency, and the pupil function we assume is a fairly smooth function. So we can neglect the impact of the pupil here to say that the impulse between the input at the front focal plane and the output at the back focal plane has this form. So a simple Fourier transform kernel between the what's happened here is that in our Fourier transform of the Fresnel kernel is the Fresnel kernel. So we're going to square the spatial frequency there, which is proportional to x naught plus x double prime. And in that square, we'll cancel with the quadratic phase terms that we had drawn out of the of our impulse response. Those terms will cancel, and we'll get a simple Fourier transform kernel for the impulse response between the input plane and the output plane. So as expected, if, for example, we had an impulse at x naught, we would get a harmonic term with a frequency proportional to x naught over lambda f at the output plane. Now, if we take this impulse response between the input plane and the output plane and express a relationship between an arbitrary field distribution in the front focal plane and an arbitrary field distribution in the output plane, we find that it has this Fourier transform relationship. So this is the feature that Professor Vanderlugt exploited in his optical signal processing, that the relation that we can take a Fourier transform of an input field simply by propagating from a front focal plane to the rear focal plane. Now, we've already seen that the Fraunhofer relationship, that the field that propagates from a object plane to a far field is the Fourier transform of the input field. And here with the lens, we've sort of brought the Fraunhofer regime into the macroscopic world, or into the physical world, by finding that relationship between the conjugate front focal plane and back focal plane of a lens. This effect was used in a wide variety of optical signal processing systems. Here's an example from a group at the National Institutes of Standards, where they built a Vanderlugt correlator, which is a device where we take an input plane. Here, the input spatial light modulator have a Fourier lens that's going to Fourier transform the input plane onto the back focal plane of the lens, and then you can put a computer-generated hologram or any other kind of optical modulator here that will modulate the Fourier transform of the field. And then if you Fourier transform that again, the product of two Fourier transformed is the convolution, so you can build a filter to operate on the input beam. And here, this filter is observed through several different paths, which allow a detection of the input, the spectrum, and the correlation, which you could use in signal processing. In this particular case, it was used to recognize fingerprints. So you put a fingerprint on the input plane, and then you analyze this correlation signal on the output plane. This is work from about 25 years ago, when it was still interesting to think about how you would build this kind of device optically. This achieved about 70% recognition of fingerprints, which is not really competitive with what you could do with fingerprint analysis with digital systems today, but as mentioned in the introduction, the idea of implementing optical correlations as components of neural processing remains a topic of some interest. Okay, so that's just a thing of some interest, that as we go from focal plane to focal plane, we will take these Fourier transforms, and of course we could build a 4F system with two lenses where we would Fourier transform from the front focal plane to the back focal plane, and then Fourier transform again to form an image, which is done in this system. After this second Fourier transform lens, then what you observe on the CCD here is the image of the input signal. Let's return to the impulse response and look at another condition between the input plane and the output plane. And here we'll choose 1 over z1 plus 1 over z2 equal to 1 over f, which will set this term equal to 0 and remove the quadratic term from this interval we have for the impulse response. This, of course, is the thin lens imaging condition that we previously derived in episode 25 for a condition where we'll get an image of f at the output plane. Now, the impulse response for this system, with this quadratic term removed, has this Fourier transform kernel, where now the spatial frequency is x naught over z1 plus x double prime over z2 times 1 over lambda. So this is a Fourier transform kernel with that spatial frequency operating on the pupil function. The impulse response then, with the quadratic term removed, is this Fourier transform kernel operating on the pupil function with these phase terms out in front. Now we can simplify this system a little bit by working in reduced coordinates, where we notice that we can have this little bit complicated term in x naught over the object distance and x double prime over the image distance. We would like to get rid of the scaling factor between x naught and x double prime, so that we can represent this transformation as a convolution with an impulse response. And we're partially successful in doing that. So we'll define this reduced coordinate x sub r, which is the magnification m times the object space coordinate, and m is defined as the negative of the image distance divided by the object distance. And in this reduced coordinate, then this Fourier transform of the pupil function can be turned into a fairly nice and elegant impulse response but we still have these phase terms out in front that we'll have to worry about in just a second. So this h sub r is the Fourier transform of the pupil function evaluated at the spatial frequency x over lambda d, or x over lambda f if di happens to be the focal distance. Commonly, the pupil function we assume to be a circular function with radius, or with diameter a. So we have the impulse response is going to be the Fourier transform of this circular pupil, which is the Jink function, scaled by appropriate coordinates to manage our energy conservation. Here's a plot at the bottom of what the pupil function might look like. The pupil function is 1 from minus a over 2 to a over 2, and then 0 outside that region. We have a circular pupil here. Now in Fourier space, this corresponds to spatial frequency u is going to be a over lambda f for the maximum value of x in the pupil space, or x prime in the coordinates we had just a second ago. And so here we see that the transfer function for the imaging system extends from minus a over lambda f over 2, because the pupil function goes from minus a over 2 to a over 2. And we define the f number of the system to be f is equal to, the f number is equal to the focal length divided by the aperture, which will be a number always between 1 and infinity, and typically somewhere between like 1 and 10. But this lambda f number is a typical parameter for evaluating imaging systems, because, first of all, the range for a coherent imaging system in frequency space is going to go from minus 1 over lambda f number divided by 2 to plus 1 over lambda f number divided by 2. And then if we take the Fourier transform of that, we get this Jink function, which is shown here. The extent from 0 to 0, the Jink function here happens to be 2.44 times lambda f number. So the lambda f number is a typical parameter for estimating the blur of a coherent imaging system. So if we go back to our impulse response analysis, we find that if we can consider just this coherent impulse response, the Fourier transform of the pupil function, that the field that we measure in the output plane of an imaging system is the convolution of the impulse response with the magnified version of the object, and that the transfer function is proportional to the pupil function evaluated at spatially at the spatial frequency of the system times lambda di, where di is typically going to be close to the focal length. And then the Fourier transform of the output field is just the product of this circular transfer function with the field distribution of the object. So we're ignoring for the moment these quadratic terms out in front of the imaging system, but we find that we have a filtering operation in imaging. So if we image with a circular pupil, we have this limited range over which the transfer function operates. And so this is going to be, P is a circle centered on the low frequencies that's going to modulate the spectrum of F, and band limited. It reduces the band pass. So we have a band limited system, which is characteristic of almost all imaging systems. The effect of the imaging process is to limit the bandwidth and therefore blur the object. Now, in coherent systems, the pupil function could have any form. So it could actually look like this. We could make an annular pupil where we block the center frequencies. And so here, the pupil function is 1 in the region that's black up here, and here's a cross section of it down here. If we take the Fourier transform of this, we find that we have a modulated impulse response that we'll look at. And here it shows 1 over wavelength, so that really should be a lambda f number. The effect of this is the high pass filter. So if we image the system as shown here, for example, we have a chirped field shown here, and then here's another input object, which is a square. If we image this with a conventional imaging system with a clear aperture, the effect is to low pass filter. So here we have the object field going to higher and higher frequencies, and you see that the frequencies are damped out so that the low frequencies are passed with better modulation than the high frequencies, and so we see less contrast in the high frequencies. And here, a square has a very, sharp impulse at the edges, and what you see here is ringing at the edges associated with reduction in the high frequencies. In contrast, if we image with the annular aperture, you would see this bandpass filtering, so that the low frequencies are blocked by the center of the aperture and high frequencies come through. So as we saw with the Vanderlugt filter, with coherent systems, it's possible to apply filters to the system. And those could be low-pass filters, it could be matched filters, but we can do this kind of optical signal processing. Now, this has all been ignoring these quadratic phase terms that are out in front of the coherent system. Now, in coherent systems, phase is just an essential and very dramatic part of the imaging process, and they're very, very sensitive to small phase modulations, which is the origin of speckle, among other kinds of effects we see in coherent systems. So we need to consider the impact of these quadratic phase terms in a lot more detail, and we'll do that in the next discussion.